All right, I think we have pretty much everybody in. Uh, I'll just get started with our general introductions and we'll see who else decides to join us. So for those of you who may be new to DCPL, we are Washington, D.C.'s citywide nonprofit founded in 1971 that is dedicated to preserving, protecting, and enhancing the historic built environment of the nation's capital. I have just a few things to go over before we get started. First, I'd like to start by taking a moment to acknowledge some of our top sponsors whose annual financial support helps underwrite free programs like this one today. They're the DC Commission on the Arts and Humanities, QTAC Rock, Douglas Development Corporation, Antunovich Associates, Buyer Blender Bell, Building Innovation Hub, EHT Tracers Inc., KCE Structural Engineers, and Quinn Evans. Thank you all for your dedication to historic preservation in DC. Moving on, we have just a few notes on how today's webinar is going to run. If you have a question, please use the Q&A box, which is found at the bottom of your screen. We'll go through those questions towards the end of the program. The chat will not be available during the presentation because it can be a bit distracting, but we'll open that up for discussion or comments once we enter the Q&A period. For those joining us on Facebook, Isabel will be monitoring any questions you might have, and she'll send those our way over here on Zoom. And now that we've covered that, I'm so pleased to introduce you to today's speaker, Andy Thoma, who's Grunley's Director of Virtual Design and Construction Services. Andy brings 27 years of experience in technology to strategically improve the construction process. In his role, he ensures that cutting-edge technology enhances Grunley's ability to deliver projects faster, more cost-effectively, and with a greater level of quality. So I will stop sharing my screen and I will let you share yours, Andy, and I will hand it over to you. Thank you for being here.
Great, thank you for the introduction. Like Shay said, my name is Andy Thoma. I'm here at Grunley to try to figure out how's the best way that we can use technology in historic preservation. You know, one of the things about me is I love trying to solve problems. I love technology, and I like to figure out how things are built, how things are put together. And really, that's where my passion lies in all of this, is figuring out how can we put all this together, how can we use technology to build better, and especially preserve or restore facilities that need it. Just to explain how we do that is talking about a little bit about what we do as a company. Grunley, we do a bunch of work in the DC area, and specifically we do a lot of historic projects. So what that means is we're given a lot of challenges of how do we protect the historic nature of buildings, how do we build it, how do we construct it without changing the character, the quality of the building, or more importantly, if something's damaged, to do no more damage to it and help preserve it and protect it. And that's really where I get that opportunity to do what I really love, which is to get into the technology, to be able to get into working on these projects and utilizing the technologies and the different techniques on them that we're going to talk about today. What I would like to do today is go through a few different things. Virtual design and construction, or BIM. I'd like to go through a case study of the Carnegie Library renovation we've done, also the Milken Foundation Museum and Conference Room, and then just kind of touch on a little bit of future technologies that we're going to see in this historic preservation space in the future. So with that, I need to cut into an explanation of really what this concept is of virtual design and construction, and what the terms mean that we utilize on these projects. First off, you may have heard of BIM. If you haven't, it's Building Information Management. It's also referred to as Building Information Modeling, and that's very relevant to the technologies that we're going to talk about today. However, it doesn't necessarily include everything. For example, building coordination, where we're using three-dimensional models to coordinate a space or design that space, doesn't necessarily include reality capture or laser scanning, trying to understand existing conditions. So you're starting to see more and more people using this term, virtual design and construction. VDC really incorporates more of just BIM. It actually incorporates all the different processes, and more importantly, allows us to have these technologies grow on their usage on these different types of projects. To kind of get into that, I'm going to break it down into the individual technologies themselves that are all encompassing of this technology or process, and kind of go through what each one of those do. And then I want to talk about some specific examples of how we are doing them. First one I want to talk about is the idea of doing VDC or BIM as it takes from a designer to a constructor. We're a construction company, so obviously I care a lot about what the construction of the project looks like. But what you're going to be getting from a designer or someone that's going to be worrying about the building is going to be a model of the space, three-dimensional representation of exactly what's being constructed. That model will then transform into different aspects of what we need to do during construction. So what you're looking at on your screen now is this is the National Zoological Park or Smithsonian National Zoo's birdhouse. It was a historic building that was renovated recently to repair damage to the building that had happened because it was of its age, and also to restore it back to some of its original condition as constructed, and to make it a current space that you can go see animals, the birds. The top image comes from the architect, and as a constructor, we utilize it. And the lower main image, where we're actually doing coordination with it, we're actually adding the systems that'll be installed. Doing that allows us to figure out how things are going to be placed into the building and how things are going to be constructed in a way that everything fits and it doesn't have any challenges during construction. Kind of an example of what we do on BIM coordination and relating it to historic preservation. We go through and we will clash objects. And this is known as clash detection, clash coordination. You also hear that term in the BIM world or VDC world. And what you're really doing is, does one object hit another? Or does that duct hit a pipe? And vice versa. Will everything fit in the ceiling? In this case, for the zoo, what we had to worry about was this historic arch. You see it on the bottom left. It's a historic mosaic that was installed inside the building. It originally was in this position that you're seeing it here. However, it was moved over time, so it was shifted in location. When they decided to rebuild this, they wanted to put it in a more prominent location. We actually walk in, you can walk through the arch, you can look into the main atrium behind it. The challenge was, this is something that we can't modify by, drilling a pipe, a hole for a switch, or have a pipe go through. So what we do during coordination is we actually make it an object that you would physically coordinate against. So something that's meant to be like a no-go zone. And that's what you're seeing here on the representation of the screen. On the right and the left is an actual model of the shape. It is an exact model of the shape, so that we make sure that when we're coordinating, we make sure everyone understands, hey, you can't go here, and we don't drill through it. We don't add an extra space. Having it as a physical representation in the model gives us the opportunity to prevent something of historic nature getting damaged during construction, because we can make sure everyone knows, like, oh, well, I'm designing this duct or I'm putting this light in. I can't go here. I have to go somewhere else. So that's one of the things that we do during BIM coordination that helps further preservation goals, is just by simply making sure someone doesn't do something wrong to the space. We're doing a combination of different technologies or techniques. It's a bunch of different software. I'm actually listing Autodesk software, but there's a bunch of different ways to go with this. But the real goal is to build a model of these spaces in a way that we can join it all together, whether it's a physical model, or excuse me, the three-dimensional model coming from a design software, to a model coming from a reality capture or a laser scan. We're putting them all together in a way that we can manipulate it and look at it and use it. And this gives us really a great chance to understand, what's the space look like? What challenges are we going to run into that space? Does everything fit? Because we know that the As-built plans are over 100 years old. Those as-built plans, they might be within a foot of accuracy, and they don't account for settling or, the walls changing during time. So the goal is you have to compensate or think about that during the entire construction process. Is the wall really where you say it is in the design model, which was based on those old as-built? Well, let's go verify it. Let's go check it. And that's really one of the things that technology has the ability for us to do, is to be able to figure out how is that going to all go together, and how is it going to fit in the space requirements we have, and what are we going to do to make it work if it doesn't fit in those space requirements. Going with that, that introduces another aspect of this VDC technology idea, and that is reality capture. Reality capture is probably one of the most important things during a historic preservation or a construction on a historic site, or even a pre-construction environment for a historic site, is understanding what you have. You can go up there with a tape measure, but honestly, you're never going to capture as much information as, say, a laser scanner is producing a 3D point cloud. Laser scanner, really simply put, is a 3D photocopier. It shoots out a laser, measures your distance, and it does it millions of times wherever you sit it. You develop this big, well-developed cloud that shows everything in there, and you can do a bunch of different things, which I'll touch about it in a moment. There's other technologies out there. There's something called GeoSlam. GeoSlam is, like most people know it as Matterport, probably because they have the biggest name in the space. But what that does is it's like a laser scanner, but it uses a lot more photography, uses LiDAR. Actually, they both use LiDAR. It just uses more of like an infrared camera, and it uses a less accurate laser than a traditional laser scanner does. What it does do is it takes amazing photos. So you actually get photos that you can take dimensions off of. It's a lot faster, but it also is the same goal as let's preserve the space, or let's try to get an idea of exactly what we have. Another big thing that's very, very useful is the concept of just site photography or progress tracking. Generally speaking, we're using a 360-degree camera, so a camera that takes a picture all the way around you. You use that because you can take a lot of pictures really fast, and it gives you a chance to explore your space and capture things. You can capture, like, say, a crack in the floor, which is a historic crack because it was there when it was built. We need to be able to preserve that. So we have the ability to photo document it, or we can see, hey, that crack wasn't there before. How do we know that? Because we documented it all the way through. So reality captures give us this ability to understand the space and be able to see the space a little bit better. When you actually are taking that space and you are capturing it, what you're doing is you're going through and you are being able to capture the exact conditions at the time of the scan. So what you're seeing here is actually that is a scan that you're going into. You can see, let me go back one. That view right here is actually the point cloud. So that point cloud is just the conglomeration of all the millions of points the laser scanner actually shot. And then if I let it go all the way to the end here, you're actually zooming into a point where you're seeing the 3D image of that space. That image is actually made up of millions of little individual 3D points. So if I wanted to, I could go in and actually measure, that window frame and get exactly every single dimension. And depending on the instrument you use, it can go down to thousandths of an inch. So it gives you a really accurate understanding of what that space is and what it looks like at the end of the day. To give you some ideas of what we would use it for, this is actually the Carnegie Library in DC. It was a full renovation of the space. And during that renovation, a lot of stuff had to be taken down and put up, had to be preserved and protected. Also had things to be recreated and actually put all together. So what you're seeing here is just the GeoSlam or Matterport scan of the original space. The idea here was we went through and we scanned the space before we touched it, so that we had an exact record of what was installed before we started. Something that we could dimension, something that we could zoom in, look at, take different pictures, and really kind of understand what the space looked like before we touched it, to make sure that everything was being put back that was meant to be preserved and put back in the same locations if it was had to be moved, or more importantly, something that was protected, that if it did get damaged somehow, we would have a record of what it was, so we could go back and make sure we try to recreate what was there. Another thing that you can do with this idea of reality capture is this progress tracking I talked about earlier. So what you're seeing is this is actually a historic barrack in Fort Myer. And what we're able to do is, capture construction as it happens and figure out what it looks like over a duration of time. It's like the ultimate truth teller. We know exactly when something changed and how it's changing and how it's being put together, and whether or not it's being put together to what we were looking for. What's interesting about this technology is you can also integrate it with the BIM model or the three-dimensional model, so you can actually do a comparison of what's in reality versus what's been installed. So you can actually look at the two to make sure that you're actually meeting the intent of what construction is supposed to be, and things are being placed exactly where they are. And then if something's not, well, you can generate that conversation of like, is this going to impact something, or, where you've got to move that because there's no way we can avoid something. And that's really the idea of this image capturing technology that's out there now. One of the beautiful things about laser scanning is that you can capture things that you wouldn't normally be able to see. What you're looking at here is a laser scan. This is the Natural History Museum in DC at the mall. Specifically, we wanted to figure out the relationship of how the door mounted to the interstitial space below the door on the mall entrance side, and because we were restoring the historic gate that was on there, and we wanted to make sure that the gate was supported from underneath, and that there was no challenges when anchors were being placed, that it actually is going to have a good purchase into something. So what we simply did was we created a laser scan. This laser scan was inside and outside of the building. So we actually went into if you know this museum, there's something called the Bard Theater, and that's actually what's on the bottom right. It's actually the back of the stage, so it's back of house. We scanned inside of there. We scanned up in the projection area that's up there. We also scanned outside. There's like I don't know, I call it a service tunnel, but it's like a access that you could walk through. It's not public facing, but it is public. You also had storage rooms. You had interstitial space, like for ducts, for pipes, for electrical, and then you had the actual public side, which is actually the top of this. Those columns there on the left are the big columns. They're the big Roman columns on the face of the building. You go through the door, and on the right, you can actually see that's people and the security scanners, the metal scanners. So, we went basically inside and outside of the building. We put together this very large scan of all that information. What's highlighted in that yellow is kind of the area of concern, and anything that you see white there, well, that's not transparent. That's actually solid material. So what we could do is figure out exactly where the door was. In this case, I'm going to hold my mouse over. We could figure out exactly where the door was over this interstitial space that was right above the theater's stage. So that, if we're going to put an anchor in here, well, we know we can't go down too far or we're going to hit something. More importantly, we could say, hey, designers, we have, I forget how much material was here, 6 inches of material. Is that going to be enough for you? What type of system do you need to design? What was interesting about this is this space all through here is actually it's like a crawl space. It's a really tiny, small space. They were able to design an anchor system that went down in and bolted to the ceiling of that, simply because we had the information of creating this big model and understanding how everything is put together. All of this related to preservation is this allowed us to, put the gate back together, make sure it's secure, and then also make sure that, this is a permanent fix to this building. You're not gonna ever have to worry about the anchor points again, because the way that they were able to design the system was by fully understanding the space that was there. So again, reality capture gives you that chance to actually cross-section an existing building. There's really no other way to see how all of this would go together without creating something like this big reality capture laser scan. So with that, I want to try to do some case studies. This particular case study is going to be the Carnegie Library in DC. So what was interesting about this space is we had a lot of renovation that was going to be done to it. First, it was going to get restored back to its original configuration. As you're staring on this picture, if you look at that ceiling above, I believe that was added in the 80s, if I'm not correct. I'm pretty sure this was an open courtyard at one time, and that ceiling was, they added 2 floors in that courtyard to close it off. The goal on this renovation was to open it back up and to put it back into its original 1906 configuration as the building was originally built. So they had to remove that. Unfortunately, to do that, that meant a lot of that wall that you're seeing in front of you was going to have to be taken down and then rebuilt in kind, but obviously without the ceiling in place. So this created a couple challenges. First off, what exactly did we have in that space at the time? We needed to make sure that you could physically do this and actually remove all of this and not compromise the structure of the building. The other thing that we really cared about was there was going to be they were going to make it open courtyard again, but now the current client wanted to enclose that space, so they wanted to put glass panels on the roofs, make a big skylight. So instead of having open air, this is now an enclosed space. So we actually had to support that, and these glass panels are super heavy. So we had to figure out how to put all of this together in that space. So taking the laser scan, we were able to understand what the shape of the space was, but we also could preserve everything that was there, every location, the width, size, put everything together. What was interesting in that is we discovered some unique challenges that we had to overcome. And the first one was that wall that you saw with the door is not center. It was historically, when it was originally built, it was off center a little bit. Everything was shifted slightly to the northeast. And that room that was getting taken apart and put back together wasn't square, it was more trapezoidal shape. And there was historic windows that actually were in that facade too. And those things were not, they didn't really have any rhyme or reason. They were not plumb, they were not straight, everything that you would expect in a historic building, in that it wasn't exactly what you expect. Looking at the as-built, of course, everything showed it was perfect. But in reality, using the laser scan, we were able to figure out, well, the buildings, that wall, if you're going to build it back and restore it back to its original shape, you're gonna have to build differently. You're gonna have to actually build it, offset, off center, and the windows need to be placed in the exact right spot. And the window size were different than we expected. So what we were able to do with our laser scan to help preserve this space was really figure out what was there, and then be able to talk to the architects and say, hey, when you design this and when we assemble this, we have to take in these existing conditions to account. We need to actually rebuild it and put it together in that way. And that's actually what you're looking at here. You're looking at the contract document or what was supposed to be the walls, and we're measuring the variations from what we saw installed versus what was actually on the plan for measurements. So to kind of give you an idea, this is an outside view that cupola or this area right here, that was what was being removed to open it up for the space for the skylights, for the large pieces of glass that went down into that, you know, the light would go down into that space you just saw a second ago. That those are the supports that we had to deal with, and you can see the extent of the laser scan we had to do on this, that we actually had to scan the inside and outside. And you can see these that personnel lift there, the cherry picker, whatever you want to call it. We actually had to ride that up on top of the roof with the laser scanner to actually scan on the roof. So, you know, it was a huge effort to get it all put together to make this really great model to understand this is what the shape of the building is, how everything is being put together. So you really can understand what you're working on and what it looks like simply by using technology to better to capture what's there and to be able to analyze what's there and actually put it all together. This kind of gives you an idea of the phases of where it was going. On the left picture, you can see they actually removed the floors to give you a concept of where everything's going. They didn't actually remove the roof yet, where the glass was going to go. Middle picture kind of shows you a slice of the model with the laser scan. You can see the 3 floors. That's the floor 1, 2 that was getting removed and taken out. And that would have been right here and right here. That's the old roof that was being removed. Then finally on the right, you can see the finished space. And when I was saying the chimney, this is actually the chimney, the historic chimney that had to be built offset. It's, you know, almost imperceivable to the eye that it is about 1 inch off, but it is to preserve it to what it was supposed to be. That's what we're able to figure out. Same thing with these windows, the location, you know, they look really similar in this one, but both windows were unique. They had a slightly different size, a slightly different location. They were not centered. So again, another thing that we had to worry about to put it all together. And not real obvious, but these are big glass panels, and there's a whole support system for those glass panels hidden behind all the walls, so that everything was built appropriately to match what was originally installed. Okay, moving forward from that case example, I want to kind of talk about some of the other technologies that are done on projects. One of the big things that we find useful on historic projects in particular is ground penetrating radar. The idea of ground penetrating radar is that it shoots out a radar beam, and it tells you what's behind the surface by what returns it sees. It gives us a really good chance to understand what's inside of historic facades, materials, floors, so that we know what we're getting into. So we know, oh, you can't drill in there. Oh, it's structurally sound. Oh, it is not structurally sound. What's putting everything together? A real great example that I have no pictures for because I deleted my phone and I'm really mad about this myself. But we were on the Jefferson Memorials, and the Jefferson Memorial project, there was scaffolding that went all the way up to the ceiling. And what we needed to do was figure out how the stone was mounted on the face of some of the beams, because some of those stone plates, easiest way to explain it is they were loose. And what we needed to do is figure out a best way to rehang it and put it back together. But unfortunately, no one had any good records of how these things were hung. So we used the handheld radar on the right, this red one, and we were able to figure out where the hanging mounts were for each one of those things. So we understood, okay, if we're going to take beam off, this is how it's being clipped into place. So that way we didn't damage any of the stone as we removed it, so they could replace the hangers and then put it back on. So kind of an example that we could use ground penetrating radar for. This is another great example. So what we're looking at is this was it's Meridian Heights. It's over by Howard University, and it was originally a one of was unattached. What was it? Unattached women dorms during World War II. So it was one of those buildings that was built for the war effort to house women that were working for the military at the time, and it was renovated into apartments. And in this particular case, these apartments, they needed to retain the historic character of the outside of the building, and then also the hallways and openings like the windows. The challenge was we needed to figure out, okay, how do we convert these into modern apartments? That meant we had to drill through the floor, add things like piping for a water heater. The thing is this was a terracotta and concrete beam construction system. We couldn't drill through the terracotta because that would compromise the structure itself. So we used GPR to find where we could actually drill, also verify the limits of where the terracotta was. So in this case, it was a historic structure of how do we preserve the structure without damaging it, but still do work on that particular structure. So that's one of the interesting things that you can do is you can figure out what's inside these beams. You can figure out what's inside the concrete. You know, where is all of technology will let you see through things that are solid. There's a newer technology that I've been investigating, looking out, and that's portable X-ray machines. And sounds exactly like what it is. It's like the things you see at a dentist, but in handheld format. Really interesting because it will give you an X-ray and it'll actually give you a digital readout, so you can actually look at it right there. It's not necessarily something that you're seeing in. It's mostly used for like border patrol, and you're checking cars for smuggling illegal things. But it's one of those technologies that it's looking like we can adapt that to understand the construction objects. So we could say that historic arch that we saw earlier, you know, X-ray, figure out, is the rebar in one piece or not, or is it rotted out inside? Can that be moved, or if I move it, is it going to crack more? So there's another idea of looking in and understanding what's inside of these materials. Another things that you're starting to see in a technology wise, this kind of goes with the concept of laser scanning and reality capture, but kind of taking that, instead of figuring out existing conditions, we'll take those conditions and recreate something that may be lost to history or time if we don't try to preserve it. So what we can do is we can use the laser scanner to get an exact model of something, and then we can try to recreate it, whether that is through additive manufacturing, or in this case, a CNC machine that actually will carve the stone, so you could create an exact replica of something that's there. Maybe the piece of stone millwork or stone decorative work is going to be cracked, and there's no way to save it in the field. Well, let's scan it so that we can create an exact replica to replace what's there. Or maybe one's damaged out of you know, it's so damaged that we need to create a new one, you know, so we pick one that's a good copy of the old one. We can go ahead and actually create that scan, which then can be turned into a three-dimensional model, which then can be fed into a machine to actually create that. Kind of going further with that, there's an example of it. This is one of the light fixtures at the US Capitol. Over time, some of these bronze angels would either damaged or lost and needed to be replaced. The challenge being, obviously, they're not something that, you know, they're pieces of art. They're all individually made. So creating another one is not an easy task if you're trying to make it a really perfect example of what was there. So what happened in this case was a representative example was picked, and that was then laser scanned. And it was if you look at the middle picture, it's the clear one that was actually 3D printed, also known as additive manufacturing. So you created a 3D print of that object. That angel then was converted into a molding blank so that someone could cast it out of bronze. And that's the like the tan colored one on the right of the screen. And then finally, it was cast in bronze, which is the one on the left, and that was aged. So that what you would have is a pretty you would have an accurate reproduction of one that was existing somewhere else that we could then use to replace and install it on the light standards, so that you never knew that there was one that was gone. So that's another idea of technology, is laser scanning and things like 3D printing are really coming into play to change how we restore objects that are broken. Another example of technology that is out there that can be used for preservation and restoration work is this concept of laser cleaning, laser ablation. So if you saw the Jefferson Memorial a while ago, it was dirty, like the picture on the left. If you look at it now, it's all shiny and white. What basically is growing on is mildew. It's called, its fancy name is called biofilm. But essentially, you had growth on the rock that was changing the color of the rock, and also changing the nature of the rock because it's mildew stuff growing on there. There's also bugs on there, something called a mud dauber, and they just build little nests on there. But if you steam cleaned it, it would clean it off pretty well, but it wouldn't get it necessarily perfectly clean. So they did something called laser ablation. Laser ablation is using a laser, and laser light changes essentially heats up the biomass or the biofilm, and turns it to all the powder. So what it's doing is it's turning you set it in such a way that it will overheat the biomass. Biomass essentially dies, burns, if you want to think of it that way, but it doesn't affect the stone itself, because it doesn't get the stone on, it only gets the biomass on. It's again going with the setting. So that's being utilized as a technology to actually clean off and clean some of these types of different stones. So it's another example of technology and construction that can be used. To kind of get into another case example of some of the technologies that you can use in the project, I'd like to talk about the Milken Museum of the American Educator. A lot of people will also refer to this MAE. It's also the Milken Museum and Conference Center. I've heard about 4 different names for this building, but I'll call it the Milken Museum because it's pretty straightforward. So a couple interesting challenges we had on this building that we use technology in a successful way to help construction. The first one was the elevator shafts. On the left-hand side, you see a picture looking down in the elevator shaft. The challenge we had was they wanted to keep these beautiful Art Deco facades on the elevator doors. And they also had this really, really beautiful mail slot that you can see in that center picture. But the challenge was they wanted to put a larger elevator car in that shaft. When we first looked at that shaft, what we immediately figured out was it may not work, and that car may not fit inside this shaft. So what we did was we actually took the laser scanner and we rode up and down the actual elevator car with it to scan the entire shaft. When we scanned the entire shaft, we created something that you're seeing on the screen. A lot of people call these heat maps, and it's not necessarily what they are. They are floor leveling reports or plumb reports. On the right-hand side, you can see the floor plates. That's actually the floors of the building. What this is showing you is how level the floor is. How high does it deviate from a fixed elevation, up or down? And each color represents a variation in that. So you can tell how far the slab goes down or up, and you can figure out how much material needs to be added, or if so much material is added, how much you can remove, that kind of thing. On the left, the vertical ones, what you're looking at is the same idea, just applied to a vertical surface, so a plumb report. What we were able to figure out inside of these shafts, elevator shafts, was that they were smaller than we thought. More importantly, the surfaces, they kind of went in and out. So what we had a challenge was if we were going to put a car, the car would have to fit in that smaller space. And so that smaller space had to be taken account of so that we could figure out how it all goes together. So what they had to do was redesign the elevator cars that they were putting in there. And utilizing this report, they were able to figure out what's the efficient size or maximum size that we could put everything back together and put everything back into its place on the outside, but yet fit on the inside that elevator. So you can actually see there's another example of that report on the left, and then you can see the actual final picture of that same space while it was done. And the advantage was we were able to preserve the historic facades of that elevator lobby and the elevator doors and everything. However, we were able to put a larger, newer car that would fit inside that building because we utilized the laser scan and model technology to figure out how everything's going to be put together and how everything's going to fit. Another thing that this building was interesting in its construction was that they were putting a theater essentially in the basement. The challenge is the basement really didn't exist where they wanted to do that. So they had to dig down into the basement and create that space. So that meant you had active excavation under the building, and you had to support the building while you're removing that material and pour new footers and micropiles inside that space. All of that's going on when you have that picture in the center. There's a historic ceiling that's being kept and preserved. At the same time, all that other construction is going on. So you not only have the potential of the building collapsing underneath you because you're literally digging a hole underneath it, but you also have the challenge of how do you not damage anything by worrying about the building shift while you're doing that construction. So an interesting part of this project was using technology to really understand what the project looks like. What you're seeing is another aspect of technology can be used. We create a three-dimensional model of the space so we can really understand how are we going to build this building? How are we going to construct it? So create a logistics plan, but then also a model to really grasp how are we going to dig and support and get the personnel and get everyone together. So we look at this as a huge plan to put everything together. Some interesting things about this, they believe they were the largest steel columns installed a building in DC, if I remember correctly. But what you're watching is kind of the sequence of how everything is being put together to preserve and hold that space together. Also, how do you do that logistically and not damage any of the other building inside or out, or disturb any of the neighbors as you're doing that construction. So utilizing a BIM model, this three-dimensional model, and putting it all together, we're able to really get a concept of how everything is going to be together so we can do a much more deeper planning process, understand the logistics, and put that all together. This is really great for also selling to clients, owners, and the neighbors. Hey, this is what we plan on doing, just to let you know, this is how the construction process is going. During construction, you're kind of seeing a time lapse here on the right of that space as they're digging this out and actually doing that creation. During construction, it gets a little different as far as you need to figure out how things are working and how things are being put together. So one of those big thing that you can use technology for is progress tracking, understanding how it's put together, how everything is being assembled, what different ways of construction are being used most effectively. And that's kind of what this lower right is. it's not as, this is a simulation of the construction, the timeline of how everything's being put together. It's not super exciting because it's not as flashy as the other ones rendering wise, but what you're seeing is real-time data of this is what's being installed, this is when we're going to install it, this is what's in progress. So what I can do with this is I can take this process and I can look at it at any time and be able to say, okay, from this week to this week, we are doing this. These have been installed. This is my curing time. Now I can really drill down into the data of how I'm building this building. And I'm using the design model as my basis for this. I'm taking the design model and I'm adding that information, or I in BIM, and I'm being able to go through and do a much deeper analysis on how everything's being put together. And I can get all the way through to the actual construction, final construction of this building. So technology doesn't have to necessarily be, as flashy as the laser scan. It could also be as super useful as just being able to track the progress, to understand how everything is being put together, and to be able to validate that, so I can do a better job of making sure that my progress is being tracked. So during that construction sequence, you saw all of that digging and building. One of the big things that was a challenge was how do we keep this building stable? Is the building moving during that entire process? Is there, a concern that we've dug too far, or what's happening to the building as we're going? A lot of this comes down to using technology to monitor all this. You obviously can do seismic monitoring. So we had seismic monitors on the building to actually feel how's this building moving while construction was going on, and see if there's any shocks to the building. Other thing, there was humidity sensors, because obviously humidity is going to change the building, that could change the shape of the building, and that might cause an issue. So we want to understand how are the walls put together, how are they moving. The other thing that was done was surveying, or the concept again of reality capture. So using a regular survey instrument, measuring fixed points on the walls tells us, hey, this is moving, or this is shifted in and out. Laser scans can be incorporated also. What you're looking at on the bottom right is a laser scan giving the what's the wall shape. We can monitor this over a period of time by doing more than one scan and overlaying them on each other and saying, has the color changed? Is the blue now turning to red? So that means the wall is either bowing or in or out. And we can really do a better job of tracking how the construction of the building is going to go. Two real quick slides that I want to get into is some of the future technologies you're going to kind of start seeing in construction. One of those things is going to be this concept of augmented reality. So you're going to be able to walk up to a project, phone, iPad, or maybe the new Apple Vision Pro type thing, or the HoloLens from Microsoft. But you can look at the space and see what it's going to look like. So in a preservation standpoint, you can see, okay, what does construction look like? I can sequence the whole thing, and you can watch construction on the space, and you can say, oh wow, that's going to do great, or I'm going to see a problem at this spot because of the way they have to get something in there is going to potentially damage a historic facade or something to that nature. And you'd be able to understand all this in a simulated environment before it happens. So I can see, oh, okay, this is how construction is going to go. And I can actually go through and look at that the whole way through. Other thing that we're going to start seeing more of is this rapid 3D printing or additive manufacturing. You're going to see these devices on site, not like the other ones where you're going to see them off site. You're going to actually see things custom made in real time and put it in. So you'll want to install a support, you laser scan it right there, you actually make that object right there, and you install it right away. So there's zero time turning around, putting things into place. But more importantly, I want to prototype how that support's going to fit in. I'll print it. If it works, great. If it doesn't work, well, I'll just print another one because I have the machine there. I have the ability to create that there. So you're going to have the ability to do more custom work, which is particularly important for, historic structure, because again, the historic structure won't conform to probably the as-built, because the as-built are not that accurate when they were made. I don't know, 100-year-old building, the as-built are just not as accurate as what the space is, unless someone goes through the time to check all of that. Instead of worrying about any type of delays because of finding unforeseen conditions, well, now you can actually make custom-made parts right then and there to replace things, to try things, and to put it all back together. So with that, I am happy to answer any questions you all might have.
Great job, Andy. Wow, I know I learned a lot, and I have a few questions, but we also have questions from our audience members. So we have one. Are students in architecture programs learning about this technology, and are there special preservation architecture certifications for different architects or firms that might verify, a new familiarity with these techniques?
The quick answer is yes. There are a lot of architectural schools. You'll also find it in engineering schools too, in particular with construction, coming from my experience and background, that you see people being trained specifically in how BIM works, but then all the different assets that BIM can bring to us and all the different things that 3D modeling and this reality capture helps us. If you look at a lot of the thought leaders in this space, a lot of them are from universities, and a lot of them are in training programs or have programs in regards that. As the answer to the specific certification, that I'm not entirely sure about. I think most of is a school going to have that right now? I don't know. Should they? Probably, because one of the big things is it's actually really easy to make a model. It's really easy to create a reality capture. It's really hard to make them effectively useful. Experience really helps there, and training really helps there. Understanding the process of joining all of those together, that's definitely a challenge for anyone doing this. I would think one of the things that we would love to see is being able to train people and to have a certification saying, yeah, I totally understand, BIM models and reality capture, and I want to combine those two. So
yeah, great answer. This is a kind of related question, but how long have construction companies been using this sort of technology?
I'd say that laser scanners themselves have been around for probably about 20 plus years. Now the challenge is their cost. They used to be gigantic, and they used to cost way more than most people could afford. Nowadays they're rather small. I mean, if you think about it, you have a LiDAR scanner in an iPhone Pro or an Apple iPad Pro. So the technology is becoming more ubiquitous, and it's also becoming smaller, and more importantly, the cost is coming down. So the more people can afford it, and more people can do it. As far as construction companies using it, I would say in the past 5 years, you've seen more widespread adoption by almost everyone in the general contractor space. I don't know if you would say find it in like the, like home builder space, but in the commercial contractor world, pretty much everyone's doing it, whether that means they own one and have a program in-house, or they're hiring someone to do it. They are definitely using it in some form or another in their construction process.
Gotcha. Has there ever been a case where the technology hasn't picked up on a certain material, or you've found something unexpected, or is it pretty foolproof as a process?
I think every time I do something, it picks up on something new, and something unquestioned. It's usually the challenge of the machines will pick up on it. It's whether we as humans can interpret what the machines are giving us. And I find that we do get more experience every time we run it, on every time we try to create it. Usually it comes down to you being able to ask the question of, what here is important to me in this capture? What is the thing that I'm trying to preserve, restore, build? And what do I want to solve? Am I just trying to make it easier for you to install something? Am I trying to make it easier to understand what's there measurement wise? Or do I need to know, okay, what is the internal structure of this object and what materials were used in this object? And is there any internal damage or something to that nature? Once you can ask that question, then you can come around and go, okay, I need technology to do this, this, and this. And then you find the appropriate method or possible, machine that can actually do what you're looking for.
Great. We have another question about, is VDC the same as creating a digital twin?
Yes and no. Digital twin would definitely be part of the VDC process. The VDC process kind of covers a little bit of everything. If you want to think about it, it's the name that covers everything that we would do inside of that world. Digital twin is a combination of creating a three-dimensional model, collecting asset information, like exactly what's there, what type of window, what type of piping or mechanical equipment's there, and then putting it all into one format that everyone can use. So that's kind of covering everything you would do in the VDC process to create that digital twin. Easiest way to explain a digital twin is it's a BIM model that has intelligent information from reality, so that everything is combined into one big thing, and we've put everything together. If I relate a digital twin to what I showed you, we had digital twins to be able to create that integrated model that you saw for Milken, where we did the actual construction from it. So that we actually had dates and times assigned to when are things going to be installed for that building. And also in there was, didn't really show because it didn't have time, but you also had laser scans that gave you an exact replica of what that space was, so that the model could be modified and adjusted to be able to match that.
Great. Well, I think I'll leave that as our last question. And thank you so much, Andy, for answering and for being here today. And I found this really fascinating, and I'm sure our viewers did as well. So thank you, and have a great day.
You too. Thank you.
Thank you. Bye.